We're now going to discuss this idea called effective nuclear charge. And the idea works like this. First, we're going to imagine we'll just say like a +3 nucleus. So that would be a lithium nucleus. And we'll imagine just one electron circling that nucleus like this. In this case, this electron would experience a full +3 charge of the nucleus. There's nothing in the way. In a real lithium atom, though, we are going to have 3 electrons, right? We're going to have 2 electrons in the first shell, and we're going to have 1 electron in the second shell. And I'm going to draw this using a Bohr model of the atom. So we're just going to put a +3 electron here, and I'm going to draw the first shell here, and then the second shell here, at the same distance that I did this one. And I'll put an electron here, and we'll put 2 electrons inside this first shell. Now in this case, what we say is that this outer electron is shielded from the nucleus by the presence of these 2 electrons here. See, these 2 electrons, as they orbit the nucleus, they cause this electron to be not as attracted to the nucleus. They sort of block the force of attraction between this electron and this particular nucleus here. And we say that instead of experiencing a full +3 charge, this electron, as a result of these shielding electrons, does not experience the full +3 charge of the nucleus. Instead, it experiences a slightly smaller nuclear charge, which we will call the effective nuclear charge. And we're going to estimate the effective nuclear charge in this class, and we're going to estimate it with this particular equation. The effective nuclear charge is usually designated with a Z and an asterisk, and we're going to estimate what that is. We're not going to use the real specific details of doing so, but we're going to use an estimate that works fairly well. And what we're going to do is we're going to find sort of, well, what is this charge that this electron experiences? And the way we'll calculate that is we'll take the nuclear charge of the atom and we'll subtract from it the number of core electrons. So for the case of lithium, if we're going to find the estimated effective nuclear charge for the outer electrons, the valence electrons in lithium, what we do is we take the atomic number of lithium, which is 3, and then we'll subtract the number of core electrons in a lithium atom, which is 2. Now, you may not be able to see that real easily, but if we write out the electronic configuration of lithium, we see we have 2 electrons in the 1s and 1 electron in the 2s. 2 in the 1s and 1 in the 2s. So we see in this case that there are 2 core electrons, and 3 minus 2 gives me an effective nuclear charge of 1. And so what that means is, with these 2 electrons in the way, shielding this outer electron from the nucleus, this electron, in a sense, feels a +1 nuclear charge rather than the full-blown +3 nuclear charge that exists in the actual nucleus. Let's do this for a couple more elements in the second period. So we're going to find Z star for quite a few of these elements. And so what we'll do here is we'll say, okay, here's the estimated effective nuclear charge for lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. We'll go all the way across this second period. And we've already calculated the estimated effective nuclear charge for lithium as 1. So we'll write that in here. And now we'll calculate it for beryllium. So for beryllium, I'm going to first take the formula for the effective nuclear charge, Z star estimate. That's going to be the effective the nuclear charge on beryllium, which is 4, and we're going to subtract from it the number of core electrons. So that's going to be 4. Well, how many core electrons are in beryllium? We can figure that out from the electronic configuration. That's going to be 1s2, 2s2, and so we see that there are 2 core electrons in a beryllium atom. So if I take 4 minus the number of core electrons, which is 2, I get 2. So that's going to be the estimated effective nuclear charge for beryllium. So if I were to sort of draw the Bohr model for beryllium, we're going to put a positive 4 nucleus. We're going to have 2 core electrons in the first shell, and we'll also have 2 electrons in the valence shell. And this valence electron is going to experience not the full positive 4 on the beryllium nucleus, but rather it'll be more like a +2. And this electron is the same way. It won't experience the full positive 4 on the nucleus that exists in the beryllium nucleus, but it'll be more like it experiences a +2. Now we can calculate the same thing for boron. I'll just draw the electronic configuration first, 1s2, 2s2, and then a 2p1. Just to show you here, 1s2, 2s2, 2p1 for boron. And once again, we notice that there are 2 core electrons in in boron. So for boron, if we want to find Z star estimate, that's going to be the nuclear charge, which in boron is 5, minus the number of core electrons, which is 2. And so the estimated Z star for boron is going to be 3. I'll just plug this up here in our table. And you might notice all the way across this second period, the number of core electrons is 2, right? Because in the first 2 electrons go in the first shell, and in this period, we're filling the second shell. So these are all going to be valence electrons in this particular when we're filling this particular row of the periodic table. So I'll just do neon for you so you can see it. So if we're going to do neon, we'd have 1s2, 2s2, and then 2p, 1, 2, 3, 4, 5, 6. So even all the way across this portion of the table, we still see that we just have 2 core electrons for all these elements across the second period. And so for neon, if we wanted to find Z star estimate for neon, we would take the number of the nuclear charge, which is going to be 10, that's our atomic number, and we'll subtract the number of core electrons in neon, which is 2, and we get an effective nuclear charge of 8 for neon. And you should go through and do these calculations so that you understand that the estimated effective nuclear charge for carbon is 4, for nitrogen is 5, for oxygen is 6, and for fluorine is 7. Now, what's the big deal with this effective nuclear charge? Well, we can use it to predict what the relative sizes of these particular atoms are with respect to one another. So it'll work like this. If we imagine a lithium atom with a +3 nucleus, and it's got those 2 core electrons, and then it's got 1 electron out here, This is the valence electron, and we want to know what is the charge on the nucleus that this valence electron experiences. We see it's got a Z star of 1. So in a sense, this electron feels like it's being attracted to a positive 1 nucleus. And that's not a very strong attraction. I mean, plus 1 is much smaller than a positive 8. This is going to be pulling 8 times harder on an electron than this. And so you'll notice that I've drawn this second shell out kind of far because this plus 1 effective nuclear charge is not very good at pulling that electron in. If we do the same thing for neon, I'm going to draw my, my plus 8. Then for neon it would be plus 10 for the nucleus. It would be. And then we're going to have 2 electrons orbiting in the core 1s shell, in the first shell, and then around that we're going to put 8 valence electrons. Again, I'm doing the Bohr model here, so let's do 1, 2, 3, 4, 5, 6, 7, 8. And in this case, you'll note that 10 looks terrible. Let's make it like that. There we go, plus 10. And in this case, we see that the effective nuclear charge is 8. What that means for neon is that these particular electrons out here, this electron right here, feels like it's being pulled by a nucleus that has a charge of plus 8, which is 8 times as big as what this electron experiences in lithium. And what that means is that in this case, in a neon atom, these outer electrons, these valence electrons, are going to be much, much, much more strongly attracted to the nucleus than is the case in lithium. And that's why I have drawn this second shell pulled in more tightly, because these electrons are going to be more tightly attracted to this big honkin' plus 8 effective nuclear charge, even with these shielding electrons, than is the case with lithium. And we see as we go across this period that the effective nuclear charge increases. Again, we're estimating, but nevertheless, this effective nuclear charge increases as we go across the period. And so what we would expect as we look at these elements as we go across that second period, because the effective nuclear charge increases as you go across the period, we would expect that the sizes of the elements would get smaller and smaller and smaller and smaller and smaller and smaller as you go across the period.